solution of the differential equation x plus y into dy by dx is equals to 2y. We can write this differential equation as dy by dx is equals to 2y minus x by y. Clearly we can say that the given differential equation is a homogeneous differential equation of order 1. Now, in order to solve the homogeneous differential equations, we have to take y is equals to vx. Now, if we differentiate, it will be dy by dx is equals to v plus x into dv by dx. Let us substitute all these values in equation 1. If we substitute, it will be v plus x into dv by dx is equals to 2vx minus x by vx. And if we simplify, it will be v by v minus 1 whole square into dv plus dx by x is equals to 0. It is nothing but v dv by v minus 1 whole square plus dx by x is equals to 0. That implies if we integrate, it will be v minus 1 whole square dv plus dx by x is equals to some 0. As we have added plus and 1 to the numerator, we'll simplify this. V minus 1 by v minus 1 whole square will be dv by v minus 1 plus dv by v minus 1 whole square dv plus dx by x integral is equals to 0. 1 by x dx, integral 1 by x dx is nothing but log x. And similarly, integration of dx by x square is nothing but minus 1 by x, which is minus 1 by v minus 1 plus integration of 1 by x is log x is equals to some constant. And if we simplify, it will be log of y minus x is equals to c plus x by y minus x. So, which is option B.
For an 8-bit D2A converter having a reference voltage of 8 volts, the least significant 4 bits of the input are grounded, and the most significant 4 bits are driven by 4-bit data from binary counter. The maximum obtainable peak-to-peak amplitude of a wave at the output of the D2A converter. Here, D2A converter is having 8 bits as input, means n equals to 8 bits. So, the step size equals to, that means the resolution equals to the reference voltage divided by 2 power 8 minus 1, which is equals to approximately 31.37 millivolts. So, the digital D2A converter having 8 inputs, that means 0, 0, 0, least significant 4 bits are zeros and upper 4 bits are ones, which is approximately in decimal equals to 240. So, the analog output voltage V output equals to 240 into 31.37 millivolts, which is equals to 7.5 volts, which is option D is correct. Question is the minimum number of logic gates required to implement the following Boolean function. See, if we simplify the following Boolean function, we will represent this Boolean function as AB bar. If we take AB bar as a common, CD bar plus C bar D plus, if we take A bar B as a common, CD bar plus C bar D. So, AB bar C exclusive D plus A bar B C exclusive D. If we take C exclusive D as a common, then we will get A exclusive B in the bracket. So, we can draw this following Boolean function with one AND gate and two XOR gates. Hence, option A is correct.
He has given a 10 volts voltmeter has a resistance of 100 ohm. Okay, now it is a 10 volt voltmeter, 0 to 10 volts range. It is having a resistance of 100 ohm. Okay, now it is to be converted to 100 volts. The value of series resistance required it. Okay, now let us take, this is 100 volts should be applied. If you want to extend the range of 10 volts voltmeter, we have to connect a series resistance, okay, which is in series with the voltmeter to increase its range. Okay, now what is this one? Vm by Rm, it should be equal to Vsc by Rsc. Okay, now what is Rsc here? Rsc is equal to Vsc times of Rm by Vm. I can write VSC as V minus Vm into Rm by Vm. Okay. Now what is this one? Rm by Vm into V minus Vm. Okay, which is equal to V minus Vm is 90 into what is Rm value? Meter resistance is 100 ohms. Now what is Vm? Voltmeter range is 10. Okay. Now what is this one? We have to connect 900 ohms in series to that of voltmeter. So option is C.
Is the phase crossover frequency associated with a feedback loop employing a proportional controller. The process represented by a transfer function Gp of s equals to 2 e power minus s by tau s plus 1 whole square is found to be 0.6 radians per minute. Find the time constant is. Here, see, if we comes to options, A is 1.14, B 1.92, C 3.23, D 5.39. See, phase crossover frequency is nothing but a frequency where a phase function of a given network attains pi radian, that is minus 180 degrees, that is minus pi, is equals to the phase function is minus omega to tan inverse of 0.6 tau. Okay, everything is given in the form of radians, so it's not a problem at all because it is also in radians. While you are calculating in the calc, please keep it in radians mode, then type it. Here minus pi minus 0.6 minus 2 tan inverse 0.6 tau. So if we solve this equation, we will get tau as 5.39 seconds, which is option D is correct. The phase crossover frequency associated with the feedback loop employing a proportional controller to control the process represented by a transfer function Gp of s equals to 2 e power minus s by 1 plus tau s whole square is found to be 0.6 radians per minute. The time constant is given as 5.39 seconds. Find the gain of the proportional controller if the gain origin is 2. We know that 2k, that is the magnitude of GPS, k is the gain of the proportional controller, 5.39 omega p plus 1, this is whole square, equals to 0.5 because the gain origin is given 2. So it is equals to 0.5. Omega is nothing but phase crossover frequency, we substitute. So 2k is 0.5, 5.39 into 0.6 whole square plus 1. So if we solve this equation, we will get k as 2.87, which is option B is correct. Is a divide by n counter is designed using JK flip-flops as shown in the figure. The value of n is, if we see the configuration, this is the twisted ring counter or the Johnson's counter. If the counter is having n flip-flops, it is going to have 2 n states. So according to this statement, answer is here, it is having 3 flip-flops. So it is having 2 into 3, that is 6 states, that is our option C is correct. Question is, a divide by n counter is designed using JK flip-flops as shown in the figure. Assume initial outputs of all the flip-flops are 0. The output of the above counter is given to the circuit shown below, which consists of 3 line to 8 line decoder and LEDs. So the LEDs that will never glow are here. This is the twisted or Johnson's counter. So it is having a 3 flip-flops, means it having a 6 states, means out of the 8 states it's going to have a 6 states, means 2 states are unused states, means the ABC will never get those values as outputs. So if we give that to 3 to 8 line decoder, there are 2 lines are not going to be activated, means that means the bubble indicates 1 in normal position. O0 is having 1. So if suppose if I am giving 0 0 1 here, so O1 initially it is 1. If it is I am giving the 0 0 1 as an input to the 3 to 8 leak, O1 is selected, means that means the output at this position is 0. 0 means here is 5 volts, this 0. So the diode is going to be in conducting mode. Means here 2 lines are not going to be selected for any of the input combination, because ABC will not take two unused states. If we do the procedure or analysis what states is having, then we are going to know that D2 and D5 will never glow. Option C is correct.